In section 11.4, we're going to be talking about conditional probability. Conditional probability is the probability of an event occurring given that another event has already occurred. So we're talking about two events like we were in section 3. However, now we're talking about the probability of an event occurring given that another event has already occurred. So let's look at an example with some candies. So I'm going to have my candies here. And I have 7 cinnamon candies. I have 6 spearmint candies. Those are the green striped ones. 5 butterscotch and 3 peppermint, which are the red stripes. So I'm going to want to know, what I'm going to do is I am going to grab one candy at random, and then I'm going to want to know what is the probability that candy is spearmint, and I'm going to say given that I know it's a striped candy. So the event that's happening is that I want to know the probability that my candy is spearmint given that my candy is striped. So this is new notation, and what this means is that I'm going to find the probability that a candy that is drawn is spearmint if I already know it is striped. So this little bar here means given that. So we're going to make the assumption that the candy that I've drawn is striped, and I want to know what's the probability that if I draw a candy that I know is striped already out of this pool of candies, what's the probability that it is a spearmint candy? So the probability that it's spearmint, given that it is striped, is going to be equal to, oh, that's not a good color, the number of candies that are both spearmint and striped out of the number of candies that are striped. So the numerator is the number of candies that are spearmint and striped. The denominator is the number of candies that are striped. So the probability itself kind of gives you a hint about what to put in the numerator and denominator. So numerator is spearmint and striped. So the probability that it is spearmint, I don't think I'm spelling that right, spearmint, given that the candy is striped, would be, well, all of my spearmint candies were striped. So I'll put those guys out there. So how many of my candies are spearmint and striped? That's going to be 1, 2, 3, 4, 5, 6, all 6 of those. So that will be 6 out of the number of candies that are striped, which is 9 of them. So even though I have way more candies than 9, the probability that my candy is spearmint, if I already know that it is striped, would be 6 out of 9 or 2 out of 3. So let's look at some more examples so we can see how to set these guys up. So what I'm going to do is I'm going to draw a single card from a standard deck. And I'm going to ask you several questions for this given that stuff. So first I want to know this one. Okay, so what does this notation mean? This means that I want to know the probability that the card I draw is a queen given that the card is red. So that given that statement, the given that words is represented in the writing up here by this bar. So this bar here, I just smudged, is the given that part. So the way that I figure this out is by doing the number of cards that are, has to be both of these things. So the number of cards that are queens and red divided by the number of cards that are red. So in a deck of cards, we know we have 4 queens. We have the queen of spades, hearts, clubs, and diamonds. Only 2 of those are red. So the number of cards that are queens and red would be 2. Out of the number of cards that are red, that's half the deck, so 26 of them. So the probability that we drew a queen, given that we already know we have a red card, is 1 out of 13. Let's do some more of these. So we're still going to stick with drawing a single card. The probability that we draw a club, given that the card is black. So we need to know what's the probability that the card we drew as a club, if we already know the card is black. So we're going to take the number of cards that are clubs and black divided by the number of cards that are black. So the clubs, there are 13 clubs, and all 13 of those clubs are black. So the number of cards that are clubs and black would be 13. Divided by the number of cards that are black, that's half the deck, which is 26. So the probability that we drew a club, given that the card we draw is black, is going to be 13 out of 26, or 1/2. Now let's see what happens if I reverse that order and say what is the probability that the card I drew is black, given that I already know it's a club. So now our numerator is going to be the number of cards that are black and clubs, same as what we had in the previous problem. But now my denominator is the number of cards that are clubs. So if I already know that the card that I drew was a club, the probability that it is black would be, there are 13 blacks and clubs, out of there are 13 clubs. So if you already know you have a club, the probability that it is a black card is 1, which is the same thing as 100%. So you're guaranteed that that would be a black card. What about the probability that the card I drew is a heart if I already know the card is black? You may already know the answer to that without doing any work, but to do that formally, that would be the number of cards that are hearts and black over the number of cards that are black. Well, I know there are 26 black cards. But how many cards do I have that are both hearts and black? There are none of those cards because all of the hearts are red. So the probability that my card is a heart, if I already know it's black, would be 0, which means it's impossible. So let's formally write out the formula for the given that statement. So it's the probability of some event B happening given that I already know some event A has happened. So event A is the first thing that we already know happened, and then I'm finding the probability that B happens after that. So the way we do that is we take the number of outcomes that are both B and A divided by the number of outcomes that are A. Or it could be the percent that are both divided by the percent that are A. Or it could be the probability of both divided by the probability of A. So we have to be a little bit flexible in how we use this formula to answer different questions as we go along. We'll see that in just a couple of examples here. So our first example is going to be about ice cream. So we're going to start out knowing that 70% of your friends like chocolate ice cream. %60 of your friends like vanilla ice cream. And 20% of your friends like both chocolate and vanilla. So I'm going to ask you two questions about this problem. The first one, I want to know what percent of your friends who like chocolate ice cream also like vanilla. So what makes this a given that problem is that we're asking for what percent who already like chocolate ice cream. So this is the given that. So it's given that they like chocolate ice cream. What percent like vanilla ice cream? So we're turning this into a probability that a friend likes vanilla, given that we already know they like chocolate. Since we're given percents, we're kind of thinking back to that formula we just had. The probability that they like vanilla, given that they like chocolate, will be the percent who like both divided by the percent who like chocolate. So in our reading, we see that 70% like chocolate, 60% like vanilla, 20% like both. So the percent that like both is 20, and the percent who like chocolate is 70. So the probability that my friend likes vanilla, given that they like chocolate, or the percent of my friends who like chocolate, who already like chocolate ice cream, also like vanilla, is 2 out of 7, or, let's see, 2 out of 7, 28.6%. Another question I want to answer is, given that a friend likes vanilla ice cream, what is the probability that they also like chocolate? So now I'm kind of reversing the problem that I just had. It's given that they like vanilla. So now my probability is the probability that they like chocolate, given that I already know they like vanilla. So that will be the probability that they like both of these things. So the percent of friends who like both divided by, this one's always the denominator, the percent who like vanilla. So the percent who like both was 20%. The percent who like vanilla is 70%. Oh, that was chocolate. Percent who like vanilla was 60%. So this would simplify to 1/3. So 33.3%. If my friend likes vanilla ice cream, there's a 33.3% chance that they also like chocolate ice cream. Okay, now a different context. 43% of the kids in your class are left-handed. That seems kind of high to me, but we'll just go with it. 29% of the kids in your class are girls. 17% of the kids in your class are left-handed girls. So now for the questions. A. Given that a student is a girl, I guess that probably should say, given that a kid in your class is a girl. Given that a kid in your class is a girl, what is the probability that they are left-handed? So what I already know is that the kid in my class is a girl. So it's given that they are a girl. I want to know what's the probability that they are left-handed. So remember that based on our formula, the numerator is going to be the percent that are both left-handed and girls. And the denominator is going to be the percent that are the given that thing, so the percent that are girls. So in our class, 17% of the kids are left-handed and girls. So that's 17, and the percent that are girls is 29. So there is a 17 out of 29 probability, so 17 divided by 29, which gives me 58.6% probability that if I randomly select a student and I already know they're a girl, the probability they're left-handed is 58.6%. Part B, given that a kid in your class is left-handed, what is the probability that it's a girl? So now we want the probability, the given that part, given that a kid is left-handed, so that's given that they are left-handed, what is the probability that they are a girl? So we're looking for the percent that would be both of these things. So the percent that are both a girl and left-handed divided by, this part's always the denominator, the percent that are left-handed. So based on our reading up here, the percent that are girls and left-handed would be 17%, out of the percent that are left-handed, which was 43. So if I already know that a person is left-handed, the probability that that person is a girl would be 39.5%. So I think what you can see is that it's important to know which thing is given that, because otherwise you would get your answers incorrect if you're using the wrong denominator. So be careful that when you do your numerator, it's both of these categories, and when you do your denominator, it's that second category.